Talking about rational functions and their graphs today. So last class we studied the behavior of two new parent functions, 1 over x and 1 over x squared. We can graph many rational functions by transforming those two parents, but not all of them. Okay. So remember that also both of these parent functions have a vertical asymptote at the value of x that is excluded from the domain of each function. In both of these cases, that value is x equals 0. Right? You can't put a 0 into this function or into this function for x. And that translated in both cases to what we call a vertical asymptote. And often we draw vertical asymptotes with a dashed line, just to remind us that it's there. It's not part of the graph, it's just a guideline to drawing the graph. So we put a dashed line here to represent a vertical asymptote. So in both of these cases, we had that one at x equals 0, the excluded value from the domain. All right, so let's say that again. No, it's always going to be x equals whatever value is excluded from the domain. So in this case, you can't put 0 into either of those. But if you couldn't put 5 in, that might be a vertical asymptote. Okay, so questions about how to find vertical asymptotes. So in general, how do you find a vertical asymptote for any rational function? You look for places where the denominator is 0. Oops. We'll call that R of x for rational. And you solve q of x equals 0. Look for places where the denominator is 0. Those are going to be values that you have to exclude from the domain, and they are potential vertical asymptotes. They aren't always vertical asymptotes. All right, so how does the graph of a rational function behave near a vertical asymptote? So here's several possibilities. It can approach infinity from the right. It could approach infinity from the left. It could approach negative infinity from the right. It can approach negative infinity from the left. So as your function gets close to a vertical asymptote, it either blows up or it blows down or does one of each. So the idea is as you approach a vertical asymptote, your graph gets really, really close to it, getting really big or really small. Okay, how many vertical asymptotes does this first graph have? None. It has one what? Horizontal asymptote. This guy here would be a horizontal asymptote, but I have no vertical lines where the graph is going up, getting close to it, or going down. How about this one? How many vertical asymptotes? This one was none. 1. And this third one? 2. Yep. So a graph can have lots of vertical asymptotes, right? There is no limit, right? 0 to infinity. If you have a really complicated rational function, you could have a lot of vertical asymptotes. All right, let's see if we could identify the equations of the vertical asymptotes in these graphs. This one has none, so I don't have to identify it. But this one here, with the 1, what is the equation of that pink dashed line? X equals 2. Every point on that line has an x coordinate of 2. So x equals 2 is the equation of the asymptote. How about this guy? What's the equation of this leftmost vertical asymptote? X equals negative 2. And this one would be x equals 2. Can a graph of a rational function intersect a vertical asymptote? When y equals infinity. Okay, so yeah, if you could ever get to infinity, that's where the graph would touch the asymptote. But because you can't ever get to infinity, the graph just gets closer and closer and closer and closer to the vertical line. And the reason it can't ever touch is because you can't plug 0 You can't plug that value into the equation, right? That's how we found the vertical asymptotes. They're places where the function's undefined, where the denominator is 0. So this is a no. You can never cross a vertical asymptote. How do you indicate a vertical asymptote on a graph? A dashed line. All right. Like in these pictures. All right. One more question. Is there anything else you need to know about vertical asymptotes? Yes. One more thing. An x value, where the denominator of a rational function is 0, does not always result in a vertical asymptote. If that x value that makes the denominator 0 also makes the numerator 0, then the graph of the rational function has a hole at that x value and not a vertical asymptote. Okay, so this also tells you that your rational expression is not in lowest terms, that you could cancel the common factor. Okay. And whenever you have common factors, you have a hole in the graph, as opposed to a vertical asymptote. What is a hole in the graph? No? Okay. What's the question? Yes, you can work with a simplified equation. You just have to keep in mind, my simplified equation is going to be exactly like my complicated version of the equation, except there's a hole in it. They'll look exactly the same except for a hole. Yeah. All right, so let's look at the function x squared minus 9 over x plus 3. What x values are excluded from the domain of this function? X equals -3. Yep. X equals -3 has to be excluded from the domain. Okay, because otherwise my denominator would be 0, have an undefined value. Okay, so I want to reduce x squared minus 9 over x plus 3 to lowest terms, which means factor, 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 cancel, cancel, cancel. Okay, so x squared minus 9, that factors to x plus 3, x minus 3 over x plus 3, and I have a common factor. So this reduces to x minus 3. What does the graph of x minus 3 look like? It's a line, right? This is a line. So it turns out that x squared minus 9 over x plus 3 equals x minus 3, right? Except at one value of x, right? If I put x equals -3 into the line, I get -6. If I try to put x equals -3 into the rational function, I get nothing, right? I can't do it. So these two things are the same at every x value except when x is -3. So this is true for every x except x equals -3. So I can just graph the line x minus 3. I just have to put a hole in it at -3. So the graph of the line x minus 3, it's got a y-intercept at -3. It's got a slope of 1. So I can put a x-intercept at 3. And I will draw my line. Right? But this is the graph of x minus 3, which is almost exactly the same as the graph of x squared minus 9 over x plus 3. It's just that this one, I can't put a 3 in. I can't put -3 in. So the point -3, 6 on my graph, right here, that actually doesn't exist. So I have to put a hole at that spot. -3, 6, hole. That point does not exist on x squared minus 9 over x plus 3. Yes?
So you could, in theory, add an arbitrary more factors to both sides, and you can draw more holes in it.
Yep.
So you can almost kind of break down a algebra. Stuff that is
you found the fatal flaw.
Stuff that's equivalent in algebra causes real differences. Actually.
Yeah, it is really odd. It is. I know. It takes a long time. It took me a long time to say, like, these things are equal. Like I am 100% sure that these things are equal. I factored and canceled and these two things are equal, right? But they're actually not equal. Like when we're doing algebraic manipulations, we treat these as equal, but they are equal at every single x value in the whole real line, you know, negative infinity to infinity, except one. So one little place where those two things aren't equal, and that happens at -3. Okay? So for all practical purposes, when you do algebra, we treat these as the same when they're not really the same. They're just almost the same. They're the same almost everywhere, which is an actual mathematical term, almost everywhere. The 6 value, I plugged 6. I said, well, the problem happens at -3, right? When I put -3 in here, I can't. If I put -3 in this side, I would get the -6. -3 minus 3 would be -6. So that's where I got the -6. It's the value on the line.
So here you come, just the way you write out the equation could change whether it's a conic section or not. Seeing as conic, like a line is a conic section.
Yeah, that's true.
And a hole in the line is not. So you could completely change primitive form of the
We're blowing your world right now. Okay. Okay, so conclusions. X values that make the denominator equal to 0 can result in a vertical asymptote or a hole in the graph. Okay. You get a vertical asymptote if the X value makes the denominator and not the numerator equal to 0. You get a hole when the X value makes both the numerator and the denominator equal to 0. All right. So we're all set with the denominator. We've completely analyzed what the denominator does. Now I want to look at the end behavior of a rational function. So the end behavior of a rational function determines where or if it has a horizontal asymptote. So the end behavior of a few rational functions, and we'll try to develop some conclusions. So this guy, does it have a horizontal asymptote? Does it appear to have a horizontal asymptote? Yeah, it looks like I have a horizontal line here that my graph is approaching. And it's if I were to try to describe it with arrow notation, I would say as x approaches infinity, f of x is approaching what? 3. Yeah, it looks like 3. And as x approaches negative infinity, what y value is my graph approaching? Also 3. Good. Okay, so this one, we say yes, we think it has a horizontal asymptote. How about B? Horizontal asymptote? Yeah. There is a horizontal line that my graph appears to be approaching in the end behavior, and it is just the x-axis. Right? As x approaches infinity, my values of the function are getting closer and closer and closer to 0. And as x approaches negative infinity, my y values are also getting closer and closer and closer to 0. Okay. And how about this last one? No horizontal asymptote. The end behavior is just as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches negative infinity. So there's no horizontal leveling off. There's no line that the graph approaches. Okay, so to find horizontal asymptotes, if the degree of the numerator is less than the degree of the denominator, as in which of these 3 examples has the degree of the numerator less than the degree of the denominator? B, yeah. My degree for B, the degree in the numerator is the first degree, it's just a line, and the degree in the denominator is a 2. So B, I have a horizontal asymptote at the line y equals 0. Anytime the degree of the numerator is less than the degree of the denominator, y equals 0, the x-axis is your horizontal asymptote. Okay, just like in part B here, CB. Okay. If the degree of the numerator equals the degree of the denominator, which example has the 2 degrees equal? A. They're both degree 2. Squareds on top and squared on bottom. Okay, when that happens, when they're equal, then y equals a over b is a horizontal asymptote. A is the leading coefficient of the numerator, What's the leading coefficient of the numerator here? 9. And b is the leading coefficient of the denominator, which in part A is a 3. Yeah. So according to this guy, according to this rule, I should have a horizontal asymptote at y equals 9 over 3 or y equals 3, which is where we saw it. Okay, so this one I would say C, A. Okay. It's just the ratio of leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, like in part C, we have a 3 on top and a 2 on the bottom, so numerator bigger than the denominator, there is no horizontal asymptote, always. Okay. So some fun facts about horizontal and vertical asymptotes. A rational function may have several vertical asymptotes, but it can have at most one horizontal asymptote. And although a graph can never intersect a vertical asymptote, it can cross a horizontal asymptote. Horizontal asymptotes just tell you about end behavior. They don't tell you about what's happening in the middle. So it might cross near 0, somewhere in the middle, and then approach the asymptotes really far out. All right, so we have 6 steps to graphing a rational function. If it's not a transformation of 1 over x or 1 over x squared. Those guys you can graph by just shifting the parent functions, stretching, shrinking, whatever. Okay, so step 1, make sure it's fully reduced. Step 2, you can check for symmetry. Step 3, find the y-intercept, if there is one. And you always find y-intercepts by plugging in 0. Step 4, find x-intercepts. There may or may not be any, but you would do it by setting the numerator equal to 0 and solve. Okay. The reason you just set the numerator equal to 0 instead of the whole function is because fractions can only equal 0 if their numerators equal 0. It doesn't matter what the denominator is. 5, find vertical asymptotes by setting the denominator equal to 0 and solve. 6, find horizontal asymptotes by using the conclusions we just talked about. Compare the degree of the numerator and the denominator. 7, plot at least one point between and beyond each x-intercept and vertical asymptote, and then connect the points using the asymptotes and symmetry as a guide. So here I have a function. Let's graph it. We'll follow the 6 steps. 1, we need to reduce this as much as possible. Now my denominator does factor, so I could rewrite this as f of x equals 2x squared over x plus 3, x minus 3. Okay. However, nothing cancels. I don't have any common factors with my numerator and my denominator, so this is already fully reduced. All right, let's see. Step 2, check for symmetry. So for step 2, to check for symmetry, remember you plug a negative x in. Right? So I'm going to evaluate f of negative x. If I put a negative x in here, I get 2 times negative x squared over negative x squared minus 9. So I just replaced every x in the equation with a negative x, or the opposite of x. So when you take a negative x and you square it, what do you get? Positive x squared. Negative x times negative x is positive x squared. So this comes out to 2x squared over x squared minus 9. Is that exactly my original function? Yes, that is exactly my original f of x. So what kind of symmetry do I have? Y-axis or even symmetry. Okay, so that's good to know. That will help me draw the graph. Step 3, find the y-intercept. 3, to find a y-intercept, you just plug 0 into the function. So I have 0 squared over 0 squared minus 9, 2 times 0 squared over 0 squared minus 9, which is 0. So my y-intercept is at 0, 0. 4, find the x-intercepts. Yep, find the x-intercepts by setting the numerator equal to 0 and solving. I'm actually setting my whole function equal to 0 and solving. It's just that a fraction only equals 0 if its numerator equals 0. So I'm sort of saving you a step by telling you to just set the numerator equal to 0. The only way 2x squared can equal 0 is if x is 0. So my x-intercept and my y-intercept coincide the origin. All right, step 5, vertical asymptotes. To find vertical asymptotes, since it's already reduced, you can just set each factor of the denominator equal to 0 and solve it. All right, so x plus 3 equals 0, x minus 3 equals 0, x equals -3, x equals 3. So there's my vertical asymptotes, places where the denominator is 0. And then let's see, 6, horizontal asymptotes. Compare the degree of the numerator and the denominator. They're the same. Good. So that means that my horizontal asymptote is y equals the ratio of leading coefficients. The leading coefficient in my numerator is 2, and in my denominator is 1. Did somebody just say what? What? Okay. So the coefficient on the highest power of x, the coefficient on x squared in my numerator is a 2. The coefficient on x squared in the denominator is a 1. There's nothing there. You can just assume it's a 1. So my horizontal asymptote is at y equals 2 over 1 or y equals 2. That's the general rule when your degrees are equal. All right, what else do we got? 7, plot at least 1 point. Okay, so I'm going to save that one until after I've plotted everything I know now. All right, so I know 0, 0. I know my y-intercept and my x-intercept are at 0. I've got vertical asymptotes at 3 and at -3. -3. Okay. What else do I know? I know I have a horizontal asymptote at y equals 2. So I'll put that in. And that's all the information I have so far. So what I need is some points. I need some points like between asymptotes, between and beyond my asymptotes to help guide my picture. So let's, places where I still need to know some information. I would like a point in here, right, to know what happened. What does this graph do between this point that I know and this asymptote? Does it go up? Does it go down? I need to know what's happening. And then I also need to know something about in here, between the one point that I know and the asymptote. I know that as I get close to an asymptote, the graph either goes up or goes down. So if I had just one point in here, I could know which direction I'm heading. And then I also need a point in here and a point out here. Because I know my end behavior is that my graph is going to approach this horizontal line, but do I approach from above or do I approach from below? So I just need one point in each of those places and I'll know exactly how to draw the graph. So 7, my function was 2x squared over x squared minus 9, right? So let's pick a value to the left of this first vertical asymptote that's at -3. Pick any x value you want to the left of -3. -4, okay. So let's do f of -4, right? So if I put a -4 in here, -4 squared is 16, times 2 is 32, and then that's 16 minus 9 is 5. 32 over 5 is 64 over 10, which is like 6.4. So -4, comma 6.4 is on my graph. Point about right there. So now, because I have asymptotes to guide me, I know if I try to go to the right of that point, my graph has to go up and approach my asymptote. And if I try to go left, because I know what the end behavior is, I know that this is going to come down and approach the asymptote. So I can use those asymptotes as guidelines. All right, now somebody pick a value between -3 and 0. -2, -1, whichever. So let's do f of -1. 1's a little easier. So that becomes 2 over 1 minus 9 is -8, -1/4. So now I can plot the point -1, -1/4, which is right there. So now I know that I have to connect this point that I already knew from the X and Y intercept to this green point I just graphed, and I have to approach this asymptote, so it's got to go like this. And now I've actually done everything I need to do. I've done all my testing because I know the symmetry of this graph. I can copy the left side onto the right side, right? So I don't have to do any more testing. I know the rest of my graph has to look like this. So you get all the really like key things, get asymptotes, X and Y intercepts, symmetry. And then if you still can't picture what it looks like, if there are still questions about how to draw the graph, just plot some points. All right, I want to graph f of x equals 4x over x squared minus 1. So my first step should be to make sure that this is completely reduced. So I have f of x equals 4x over, I can factor that to x plus 1, x minus 1, but no common factors. Okay, so it's already completely reduced. All right. What do we do next? Symmetry? Symmetry, yeah. Okay, so to do symmetry, we plug a negative x in, f of negative x. So this is going to be 4 times negative x over negative x squared minus 1. 4 times negative x is negative 4x. When you take a negative x and you square it, you get positive x squared. Is that exactly the same as my original function? No. Is it exactly the opposite of my original function? It is exactly the opposite of my original function. Because you can put a negative sign anywhere you want in a fraction, numerator, denominator, or out front. So this is the same thing as negative 4x over x squared minus 1. That is exactly the opposite of what I started with. This is negative f of x. So what kind of symmetry does that indicate? Origin or odd, right? Okay, so that helps. So I only have to figure out what half the graph looks like, and then I'll know what the rest of it looks like. Let's try to find the y-intercept. You just plug a 0 in for plug a 0 in for x. And 4 times 0, if the numerator is 0, doesn't even matter what the denominator is, you get 0. To find x-intercepts, you set the numerator of the function equal to 0 and solve. You get x equals 0. All right, so I know the symmetry, I know the intercepts, I need to know the asymptotes. Okay, so to get vertical asymptotes, those are places where the denominator equals 0. So we need x plus 1 equal to 0, x minus 1 equal to 0. Places where the denominator is 0, so that would be at x equals -1 and x equals 1. Vertical asymptotes. And then look at horizontal asymptotes. We have to compare the degree of the numerator to the degree of the denominator. Yeah, the degree of the numerator is smaller, and the rule when that was the case was 0. It was when the degree is bigger that it's no asymptote, right? In this case, the asymptote is at y equals 0. Y equals 0. Because think about the end behavior. The reason for this is that as you plug in bigger and bigger values for x, because the horizontal asymptote tells you about the end behavior, what happens when x is really, really, really big. So if you're plugging in bigger and bigger values for x, like 10, 100, 1,000, a million, quadrillion, if you have a million divided by a million squared, right? Subtracting 1 makes almost no difference at all. A million squared is a really, really big number, a million times bigger than a million, right? Take away 1, who cares? And a million times 4 is only 4 million. It's still way smaller than a million squared. So if you have a fraction where the denominator is much, much bigger than the numerator, that fraction is going to approach a value of 0. Does that make sense? The value of the fraction would be really, really small if the denominator is much, much bigger than the numerator. So that might help you remember the rule. So my y values approach 0 in the long run. All right, I think that's everything that I'm going to start graphing it, and then I'll plot points as needed. Okay, so I've got a y-intercept at 0, x-intercept also at 0. Vertical asymptotes at 1 and at -1, and a horizontal asymptote at 0. So now what I need are some points to help me start drawing. Like once I have a point, I know that my graph is going to approach asymptotes, right? So I just need a point. So what do I get if I plug, say, -5 into my function? Let's write the function down here. It was 4x over x squared minus 1. So if I plug in -5, I get -20 over 24. Yeah, so 6 goes into both of those. No, 5 goes into both of those. -4, 6. I didn't do it. -2 thirds. Did I do that wrong? Oh, okay. 4 goes into both of those. So I get -5, 6. -5, 6. All right, so I have -5, -5, 6. So almost -1. There's my point. Now that I have that one point, and I know the end behavior, so from that point, my graph has to approach the asymptote, and it has to approach this vertical asymptote. So it's going to go down like that. And it can't approach the asymptote in the other direction, because if it was going to go up like that, it would have to cross the x-axis, and I know there's only one place that it crosses the x-axis. That's 0. All right, now I need to know what it does in the middle here. So I would need to plug in a value between, say, -1 and 0, like -0.5. So do f of -0.5. So 4 times -0.5 is -2. And -0.5 squared is 0.25. Minus 1 is -0.75. So it's going to be +2 times 4 thirds, which is 8 thirds. So instead of dividing by 3/4, I just did times 4 thirds. And the top and bottom are both negative, so it's going to be +8 thirds. So -0.5, +8 thirds. So -1/2, +8 thirds. That's like 2 2/3, something like that. It's right there. So that means that I go through the point at 0, and then I have to go through this point, and I've got to approach the asymptote without crossing the x-axis again, so it's got to go up like this. And now that I know I have origin symmetry, I don't have to do the rest of my testing. I could if I wanted to. I could test a point between 0 and 1, and bigger than 1, but because it's origin symmetry, I know it's going to go like this. And 5, 5, 6, something like this. So that when I fold over the x-axis and the y-axis, the two pieces of the graph coincide.